All right, the next section, 10C and 10D. 10C is about proof by equivalence. Proof by deduction moves typically from left to right, and a proof by equivalence shows that A is true if and only if B is true at the same time. A couple things to consider is to maintain mathematical equivalence, you can add or subtract the same term from both sides. You can multiply or divide both sides by a non-zero term. So that's an important thing to remember, that it has to be a non-zero term. It cannot be equal to 0. You cannot divide by 0. You can substitute for an equivalent subterm, for example, replacing a term by its factored or expanded form. All right, first example, prove that if a squared equals b squared, then a equals b, or a equals negative b. So if I start with a squared equals b squared, and I take the square root of both sides, I get a equals b. So you can see that the square root of both sides does not maintain equivalence. I didn't get this solution. So instead of doing that, I'll start with a squared equals b squared, and I'll subtract the same term from both sides of the equation. That does maintain equivalence. From here then, I can factor a squared minus b squared into a plus b and a minus b. And then if this equals 0, then either a plus b equals 0 or a minus b equals 0. And if a plus b equals 0, then a is equal to negative b. And if a minus b equals 0, then a is equal to b. So now we have shown our proof. Next example. Prove that a plus b squared minus 4 times a minus b squared is equal to 3b minus a times 3a minus b. Okay, so my first step is going to be I'm going to multiply or simplify this side of the equation. So I get a squared plus 2ab plus b squared minus 4 times a squared minus 2ab plus b squared. And from here, I can distribute. And then on this side of the equation, I can multiply this binomial out. So I get 9ab minus 3b squared minus 3a squared plus ab. And now we simplify and combine like terms. And on this side, how many AB terms do we have? I get 10AB. How many B squared terms do I have? Oops. Minus 3B squared. And how many A squared terms? You can see that I've proved that these are equal at the exact same time. Proof by equivalence. Next example, find the smallest integer, a, for which x squared plus a minus 2x plus a is equal to 0. So I want to find the smallest integer for which this has, oops, I forgot to write the whole thing, for which this equals 0 is real solutions, and that's an important part of this proof. So what do we know? Well, we know that if this has real solutions, remember the quadratic formula? If it has real solutions, then the discriminant, which is the stuff underneath the square root, has to be greater than or equal to 0. So we want b squared minus 4ac to be greater than or equal to 0. So I'm going to find my discriminant. B is a minus 2. A is 1, and C is A. And I'm going to multiply this out. And essentially what I have here is a quadratic inequality. To solve a quadratic inequality, you would solve it like you would the quadratic formula, but then you test values to see if it's true or false. So I'm going to see, does anything multiply together to be positive 4 and add to be negative 8? No. So now I'm going to use the quadratic formula to find my solutions. B is negative 8, so I'm going to do positive 8 plus or minus the square root of negative 8 squared minus 4 times 1 times 4, all divided by 2 times 1. So I get 8 plus or minus the square root of 64 minus 16, all divided by 2. 8 plus or minus the square root of 48 divided by 2. So 4. 48 can be simplified into 16 and 3, so 4 square root 3. If I divide these, I get 8 plus or minus 2 square root 3. So I have two solutions. One of them, A, is equal to 8 plus 2 square root 3, and one of them is equal to 8. Where did I get 8? Sorry, 4, because 8 divided by 2 is 4. And 4 minus 2 square root of 3. Let's find a decimal for these. 4 plus 2 square root of 3 is approximately 7.6. And when you subtract them, you get approximately 0.536. So if you look at these solutions on a number line, we have 0.536 and 7.46. If we substitute these back into our equation, we want to know where is it true. So say I plug in a number less than 0.50. Is 4 greater than 0? If I plug in 0 here, do I get a true statement? Yes. How about I plug in a number in between these, like 1? Well, 1 squared minus 8 times 1 is negative 7. Negative 7 plus 4 is negative 3, and negative 3 is not greater than 0. So this is false. This is not true. That means any value in between these doesn't work for this quadratic inequality, because remember, it's a quadratic inequality and not an equal sign. If I plug in a number greater than 7.46, so say 8, then I get true again. So this means my solutions are that A must be less than or equal to 0.536, and A must be greater than or equal to 7.46. If I go back to the original question, it says find the smallest integer. So what is the smallest integer that could work? Well, I can't be less than 0.53. I mean, I can't do 1 doesn't work, so that doesn't work, and 0.53 is not an integer. So the smallest integer would be 8. 8 is the smallest integer, so A equals 8. Um, 10D, definitions. A rational number is a number that can be written in the form of P divided by Q, where P and Q are integers, and Q is not equal to 0. The definition for an even integer is n equals 2k for some integer k. An odd would be 2k plus 1 for some integer k. Prove that 0.15 is a member of the set of integers. Ooh, I don't think I wanted that. I think I wanted, this is the set of rational numbers. So I'm going to prove that it's a set of rational numbers. To do that, I'm going to let x equal 0.15 repeating. Then, proof by equivalence, I can multiply both sides of this equation by 100. If I multiply this side by 100, I get 100x. And this side, I would get 15.15 repeating. Then I'm going to subtract the same number from both sides. I'm going to subtract x from both sides. Remember that x is equal to 0.15 repeating. So on this side, I get 99x, and on this side, I'm going to get just 15, because I'm subtracting 0.5 repeating. From here, I can divide by 99, and x can be written as 15 divided by 99, where 15 is an integer, and 99 is an integer, and so this can be written in the form of p divided by q. This is a set of rational numbers, is in the set of rational numbers. Prove that the product of any two rational numbers is also a rational number. So we're going to find two rational numbers, so let's let x be equal to p divided by q, where p and q are integers, and let y be equal to r divided by s, where r and s are integers. Then the product of these two numbers, x times y, would be equal to p over q times r over s. And when we multiply, we get p times r divided by q times s. And since p and r are both integers, then the product p times r is an integer. p, r, q, since and since these are integers, we're going to just call PR another integer P, and call QS another integer Q, and so X times Y is equal to P divided by Q. So X times Y is an element of the set of rational numbers. Last example, prove that if k is an odd number, then k cubed plus k squared minus k minus 1 is divisible by 8. So we're going to let k be equal to the odd number 2n plus 1. Then we would have 2n plus 1 cubed plus 2n plus 1 squared minus 2n plus 1 minus 1. And if we cube this, we get 2n cubed plus 3 times 2n squared times 1 plus 3 times 2n to the first times 1 squared plus 1 cubed. And if we square this one, we get 2n squared plus 2 times 2n times 1 plus 1. Running out of room. Thank goodness for notability. Minus 2n minus 1 minus 1. I just distributed this negative 1. So we get 8n cubed plus 12n squared plus 6n plus 1 plus 4n squared plus 4n plus 1 minus 2n minus 1 minus 1. Combine like terms, and 8n cubed, we get 12 plus 4 is 16, n squared, I get 10 minus 2 is 8, n, 1 plus 1 is 2, minus 2 is 0. So that whole thing simplified into this, and I can factor out an 8. And so this is a divisible by 8. So thus, k cubed plus k squared minus k minus 1 is divisible by 8 when k is odd. I should say when k is an odd integer. All right, thanks for watching.